And so without further ado, I'd like to introduce our plenary speaker. Dr. Julie Pullen is an oceanographer and meteorologist working on climate resilience and climate solutions. Her expertise spans climate, weather, and oceans, with a particular focus on Earth system modeling and observing. Currently an ocean climate tech investor with Propeller Ventures, she previously was the Climate Strategist at Jupiter Intelligence, and prior to that, she was an academic as an ocean engineering professor at Stevens Institution of Technology. She's a former oceanographer with the Navy, and she was also a science fellow at Stanford Center for International Security and Cooperation. She served in the US government in the Department of Homeland Security's Maritime Security Center of Excellence. She serves on numerous committees at state and national levels, advising on climate prediction, adaptation, and mitigation. And so, without further ado, please join me in welcoming Dr. Pullen. Julie, please take it away.
Thank you very much. All right, let's get our slides up here. Give me 1 second. I think I have to go to the next session. Oh, look, it's magically refreshing itself. Have to say, it's lovely to be back in the South. I was born in Kentucky, but it's doing a number on my hair. Hope it gets better tomorrow. It's in the next session. Ah, there we go. Wonderful. So, thanks very much for the opportunity to give some perspectives on this topic. And I also want to share more about how I came to this work. My first author paper as a scientist was actually on barnacles. And I came to that by way of reading Darwin's rhapsodic treatise on barnacles and looking at those incredibly fetching pictures that he drew of barnacles. Now, it's a bit niche, admittedly, for a high school student to get captivated by that, maybe even a grown-up. But that was my first paper, and I was completely hooked. I went on to work closely with evolutionary biologist Stuart Kauffman in the very early days of the Santa Fe Institute. He was a character, and is a character. He was the inspiration for Jeff Goldblum's character in Jurassic Park. Do you remember that crazy, charismatic, brilliant scientist? Stuart is all that and more. At that time in the Santa Fe Institute, it was the nexus for some of the early work around artificial intelligence and neural networks, and we set about applying those tools to biological systems. I went on to do a master's in applied math, where I continued the application of that tool set to areas of deep complexity, including fluid dynamics, and ultimately the most complex system of all, the Earth system. I crossed paths with renowned climate scientist Steve Schneider when I was at Stanford. He encouraged me to look beyond the relatively short time and space scales that I was focused on in my Earth system modeling and consider the broader and longer time and space horizons. He's exhorted us that we may only recognize major climate thresholds that we cross in the rearview mirror. And this has stuck with me after he's passed away. As an oceanographer and meteorologist with the Navy, I was staring at maps of the South Pacific, as one does when one works for the Navy, and I noticed this really arresting pattern of ocean eddies. I noticed that there were warm core eddies, about 100 kilometers in diameter, that were situated just off to the west side of the island of Luzon in the Philippines, shown here. But also all the way out to China, these eddies existed like that, with the warm core eddies to the north, the cold core upwelling eddies to the south. And I wondered, how did this pattern come about? How did the system develop these eddies? What I discovered is that the genesis of those eddies was actually due to monsoon surges or intensifications when the winds would blow very, very strongly, coming all the way down from Southeast Asia. What this did to the ocean is create a pattern of alternating bands of very strong and weak winds as those winds filtered through the volcanic terrain of the Philippines, 7,000 islands. The ocean's response was to spin up a pair of counter-rotating eddies, and you see that in the middle picture. The blue eddy to the south being that cold core eddy, the warm eddy to the north being that warm core eddy. And it was visible from space. We could see the imprint of these patterns on the biology as phytoplankton were drawn to that cold upwelled water in the eddy to the south, and relatively in reduced abundance in the warm core eddy to the north. I was delighted to find recently that people have seen in the signatures of these eddies enhanced CO2 fluxes. So beyond the biology, there are chemical alterations that are happening in these relatively small scale features that don't show up on global maps. On the right, you see the air sea CO2 flux that we think of when we think of how the oceans have absorbed 20 to 30% of the industrial CO2 emissions. These are the places where the ocean does that the most. It's in the high latitudes where colder water holds more gas. But you can tell from looking at the variability plot below that it's actually, the magnitude of the variability is almost half in places the main signal of flux. So there's a lot of detail that's happening, a lot of variability, even below the resolution of these types of global maps. There's much to learn and discover in this space, and we must do it quite quickly. I went on to be a professor in ocean engineering, where I continue to uncover patterns and explore what gave rise to those particular patterns. For instance, I studied extreme rainfall, I studied extreme heat events, and all the factors that conspire to create these conditions. And what I saw repeatedly is climate change was casting a much bigger shadow over these extreme events over time. Over time, I went on to include more parts of the Earth system in my purview. As an academic, I had had a joint appointment with the Department of Energy's Environmental and Climate Sciences Division, and I was a part of a field campaign in the Azores in the North Atlantic, these very remote set of 9 islands in the North Atlantic, where we examined the interaction between aerosols and clouds and the feedbacks with sea surface temperature. Aerosols are one of the more poorly represented parts of the Earth system models. And actually, there's a fair amount of change happening in the aerosol composition these days. As we do reductions in emissions and aerosols are reduced, we find that the clouds don't have as many condensation nuclei to form around, which has an impact on the reflectivity and is showing signs of even warming the planet. We'll hear more about that tomorrow. I did a Fulbright in the Philippines because I was repeatedly drawn back to islands as an extreme test for Earth system models. Suffice it to say, the variations around islands and on the land surface and the oceans provide a really, really big challenge to Earth system models, and they often break them. And I was dedicated to improving them. I taught graduate tropical meteorology to these students, and I also worked on a field site in the north of Luzon, a place where the Abra River drained the Cordillera Mountains out to a broad coastal plain. In this work, I was integrating models of the air, sea, and river systems to better improve our representation of these processes. And I found my field site getting repeatedly inundated by typhoons, just wiped away. Indeed, I learned from my time there, living in the Philippines, that the Philippines has been ranked #1 of countries most exposed to extreme weather events, and multiple indices rank it near the top or at the top of overall climate risk. These typhoons have had big impacts on the economy and growing, and also have affected not just the landscape that I came to love, but the people that I came to love. A recent survey showed that the Philippines youth lead the world in their worry about climate. Almost 50% of the youth are worried about climate, and almost 75% say that it's impacting their functioning. During my time in the Philippines, I frequently went scuba diving on coral sites that were being restored by faculty at the University of Philippines who dove with me. What I learned is how much we rely on the species and the nutrients that come from coral and the value that it gives in other areas of our economy. The reality is that one of the most enduring signals of climate change is that we face the abject loss of these vital ecosystems. This picture that you see here is by my friend and collaborator, Anda Carbuccia, who creates time shrines in places that are under extreme threat of climate change. What she does is she puts an hourglass and a skull in these threatened locations. The hourglass represents that we're running out of time. The skull is actually often misinterpreted. It's actually a trope that's been used throughout art history to indicate that we face a choice to act or not to act. I decided to act, and I made a big shift from academic climate science into climate risk. I joined a climate tech startup to lead early product development. We were pioneering the quantification of climate risk. I worked on downscaling projections from the CMIP models to create very detailed maps of the exposures that businesses would face to perils such as flooding, heat waves, drought, and wildfires, with the attendant uncertainty also included. I used machine learning, statistical and dynamical downscaling, as well as modern cloud-native tooling pipelines, working closely with the engineers to make all of this scalable, relocatable, and easy to ingest new data. Jupiter was a leader in the area back 5 years ago, but in the intervening years, many companies have sprung up to fill this space in the climate risk analytics arena and in the adjacent area of emissions management that involves carbon accounting and offsetting. I made the shift to climate risk because I wanted to contribute to galvanizing meaningful mitigation and adaptation. What I felt was that by doing more detailed climate risk analytics, we would be able to help companies disclose their exposure to climate risk and go down that path of offsetting the climate risk. Frameworks like TCFD have been very helpful for companies to examine their scope emissions and be able to offset them. I'm on the advisory board of the Global Association of Risk Professionals, which has a sustainability and climate risk certificate used by many management consultants and companies to be able to assess their exposure to climate risk. The net zero commitments, of course, help us lower and go to zero with emissions, and through science-based targets, we make those commitments more granular and bringing in those interim targets so we take action before we reach 2050. The disclosures continue with nature-related disclosures, which are set to follow in the footsteps of the carbon offsets markets and help us quantify better our reliance on biodiversity. This also relates to the 30 by 30 commitments, where the majority of countries have committed to protect 30% of their coastal regions by 2030, and now applies to the open seas as well with the BB&J treaty. This flywheel is happening, but it's not happening fast enough. As our friend David Ho has so succinctly written, we face a 1.5 degree threshold as soon as 2030. We need to be doing more. As Brad mentioned, these tipping points are prevalent and all localized. The most near-term ones of passing 1.5 degrees C are localized in our oceans. The interacting Earth system means that polar ice loss accelerates ocean circulation collapse, which then causes more warming for the coral reef and leads to enhanced deoxygenation that impacts the coral reefs. It's all linked. It's one connected Earth system. When I visited Antarctica, I was struck by how the waters of our planet renew in the polar regions. A recent paper last week by Matthew England tells us that the southern overturning circulation is slowing down and could reach a 40% slowdown by 2050. This impacts planetary cooling, the planet's metabolism, and nutrient distribution in pretty profound ways. We've always thought of the Southern Ocean as the largest sink in the ocean for CO2, but it hasn't always been that way. After the last ice age, it was a source, and we need to keep a close eye on what's happening in the Southern Ocean. The marine climate risks extend to the marine protected areas. This paper by colleagues at Oregon State University has looked at the conditions in large marine protected areas and identified that 45% of the ocean will see new conditions by 2060. That means conditions that the ocean hasn't experienced in 50 years. This most affects the Arctic and the tropics, and parameters like pH will be passed quite soon in terms of the novelty index. Oxygen is one that's in an entirely different category, and the threat that the oceans face there is worthy of extreme attention. I've written about this in Scientific American, and it really was the catalyst for me to make another big shift in my life, which was to go from climate risk to climate solutions. I had been angel investing in ocean solutions, and I decided to go full-time into investing with a brand new venture capital fund that launched last fall, that backs Ocean Ventures. We get behind people and innovations that we think will make the changes that need to happen in ocean climate solutions. A motivation for this work is to really contemplate the size of the new blue economy. These traditional sectors that need to be transformed quickly include the expansion of offshore renewables, sustainable fisheries aquaculture, transportation, decarbonization, and autonomy, and the coastal restoration and protection that gets us to 30 by 30. Rick Spenrad, NOAA's administrator, wrote a book about the new blue economy and what these transformations will deliver for us. By one estimate, a high estimate, this is a $500 billion market. The low estimate, it's a $100 billion market. These are big numbers that get venture capitalists really excited. The themes that we invest along are ocean carbon, and I've highlighted here in green the ones that connect with the rest of the session that we'll hear from today. The ability of blue carbon to create resilience in our coastal areas is a really important area for investment. In the ocean organics realm, this is where a lot of the decarbonization impacts will happen. When we replace proteins, we go to sustainable mechanisms of fishing and aquaculture, and we replace ingredients. So being able to use seaweed for packaging, for consumption, to replace plastics. In the area of ocean industrials, offshore renewable energy is growing, and not just the near shore, but also floating platforms. I'm seeing a lot more companies offering novel solutions for turbines and deployment of offshore platforms. Ocean-based transportation decarbonization, this space ranges all the way from different fuel types to electrification to capabilities for scrubbing the hulls of vessels so that it takes off all of those clingy barnacles that I spoke about at the beginning to create more efficiencies in the routes that the ships take so that they use less fuel and there are less emissions. I want to turn now and share with you some thoughts about the propelling factors and transformations that are happening to really create those surging markets that we saw for the new blue economy. At Propeller, we're really focused on helping create ocean unicorns or narwhal companies, and we think there are a lot of them to be made in this realm. Now, this is going to come across like a bit of a Tetris scheme here, but I want to tell you, talk through some of these propelling factors and how they impact specific transformations. So take seaweed for plastic replacement and consumption. So that involves looking at a particular existing process, seaweed cultivation, and expanding it to multiple use. What more can we get out of the seaweed? Can we use every single bit of it for something? And that has at its back the tailwinds, the scale of the ocean. It has information needs related to how best to grow the seaweed. It has efficiency gains associated with using more materials from the seaweed, and it has the demand for carbon sinks. One of the challenges associated with this is that in the US, at least, a lot of the seaweed farms are very localized and small, and permitting is an issue. When it comes to actually extracting more things from the seaweed, it takes a lot of capital to build those manufacturing plants and to create those pipelines to make that happen. Those are some of the obstacles to be overcome. Similarly, for offshore renewables, there are a lot of tailwinds, including regulatory driving it, but there are challenges in getting the grid stood up so that the power can make it from, say, those offshore floating platforms all the way to onshore where it's actually used. But as Brad mentioned, the potential for emissions reductions associated with these new blue economy activities is quite high. In aggregate, across each of these areas of renewables, shipping, ecosystems, and food sources, that amounts to about 20% of the needed annual emissions reductions, or around 11 gigatons of CO2 a year. We'll hear more on these topics in the deeper dives throughout the rest of this session on the marine energy dimension, the transportation, the blue carbon ecosystems, and aquaculture. I'm really looking forward to what will transpire the rest of today and indeed the rest of this conference. I want to close with some thoughts about how these types of decarbonization activities can influence the trajectory for those near-term tipping points that demand our attention in the oceans. Seaweed cultivation, those 30 by 30 protections, and blue carbon can all help the ocean sequester more carbon, counter ocean acidification, and locally preserve coral reefs and other vital habitats for fisheries. Similarly, decarbonized maritime shipping, considerations of those aerosol effects I mentioned that we'll hear more about from Kelly Wanzer tomorrow, and offshore renewables are poised to lower emissions, thereby reducing the warming and potentially put us in the position of preserving the polar ice. What I'd like to suggest is that we are in need of a framework for Earth system stabilization, that it gives us the ability to explore where activities can have the greatest impact to reverse Earth system tipping points and accelerate the new blue economy transformations that need to happen. For instance, imagine if we could design these foundation weather climate models to identify the key variables and thresholds. And I gave a keynote talk a couple months ago at the AI and Climate track at the AI conference in DC, and I met the developers of the first foundation model. This is a brand new class of neural network models that take in unstructured data. This team is a team of data scientists from Microsoft and UCLA, and what they've created is transformative. This type of framework would allow us to employ the best available parameterizations and ensemble coupled models at highest resolution. And we could train these generative AI techniques on structured and vitally unstructured data from both the past, present, and also the future. This would allow us to probe how, when, and where we could alter or deflect tipping points ahead of time with targeted mitigation steps or interventions in space and time. These tools are upon us, and we can seize them to transform tipping points into turning points to enhance our planetary life sustainment. I want to close by speaking about our shared values. My friend Catherine Hayhoe, who wrote an incredible book articulating what binds us together. She and I climbed Mount Sinai after COP27, and this is us looking relieved and exhilarated at the top of the summit. But her book, I highly recommend it because what it reminds us is that there's so much that binds us together in valuing a stable Earth system for ourselves and for our children. I lost my husband 2 years ago. I had never experienced grief that profound. My kids and I are finally able to go and spread his ashes next week. We're going to go to Israel to do that. I learned a lot of things from experiencing profound loss. One of the things I learned is that we never have as much time as we think we do. And also that after one experiences extreme loss, in retrospect, when you look back, you wish that you had done everything possible to prevent that loss from happening. I know what brings us all together here is that commitment to prevent the loss to our ecosystems and oceans on this planet, and that we all come together within the spirit of enhancing the stabilization of the Earth system. I'm so excited to be among people I've known from my past and people I will get to know in the future here this week. And I look forward to all the interactions and all the plans and all the discoveries that we will make together. Thank you very much.